Hey there, interwebs. I couldn't sleep the other night, but not because of anxiety or insomnia, it was because of math. Before turning out the light, I looked at a string of numbers, and the first four digits were 1, 5, 2, and 3. I thought, that's interesting. 1 times 5 is 2 plus 3, and 1 plus 5 is 2 times 3. This got me wondering if there are any other four-number sets, pairs of pairs, for which this is true. I started just by picking some small numbers at random, but this went nowhere slowly. I was going to have to use algebra. Let's say a times b is c plus d, and a plus b is c times d. We can rewrite the first equation for a as a equals c plus d over b. Next, we can rewrite the second equation as a equals cd minus b. Since both of these are equal to a, they must also be equal to each other. Now we have c plus d over b equals cd minus b. If we multiply both sides by b, we get c plus d equals b times the quantity cd minus b, or bcd minus b squared. Subtract the sum of c plus d from both sides and you'll get 0 equals bcd minus b squared minus the quantity c plus d. Reorder, divide both sides by -1 and you'll end up with b squared minus cdb plus c plus d equals 0. Just about anyone who took a high school math course will recognize this as a quadratic function. Now we can pick two random values for c and d and use the quadratic formula to solve for b. If you use integers, i.e. whole numbers, for c and d, you can get an integer value for b. That means a must also be an integer because we know that cd minus b is a, and you can't subtract one integer from the product of two others and not get an integer answer. Now, my keen viewers may have noticed something. Well, it is possible to have one or fewer real unique solutions to a quadratic function and often end up with two. Rather than have two answers for b, what you'll actually have are your values for a and d, since a and b are just arbitrary variables. Let's try this process for using values for c and d, which we know work, 2 and 3. 2 times 3 is 6, and 2 plus 3 is 5. We now have 0 equals b squared minus 6b plus 5. We can rewrite this as quantity b minus 1 times the quantity b minus 5 equals 0, and then it's trivial to find values of b which they make this true. B can be equal to 1 or 5, and so 1 and 5 are our values for a and b. I couldn't find any official term in mathematics for when you have two pairs of numbers that can be used in a four-variable equation this way, so I decided to make one up. I call this phenomenon transposable pairs. Now, you might reasonably expect there to be an infinite number of solutions to this equation, but you'd be wrong. 1, 5, 2, and 3 is the only solution which uses positive integers or counting numbers. Here's the proof. One of the numbers must be the smallest number, so let's call it a for convenience. If a is greater than or equal to 2, then ab is greater than or equal to 2b, and since b must be greater than a, 2b is greater than a plus b or b plus 2. A plus b needs to equal cd, and c and d must also be greater than 2, so cd is larger than c plus d. We've just proven that ab is greater than c plus d if a is greater than or equal to 2, therefore a must be 1. Plug that in and we get b equals c plus d and b plus 1 equals cd. Subtracting 1 from both sides of the second equation gives us b equals cd minus 1, therefore cd minus 1 equals c plus d. We can rewrite this as cd minus c minus d minus 1 equals 0. I'm going to add 2 to both sides, which gives cd minus c minus d plus 1 equals 2. We can rewrite this as quantity c minus 1 times quantity d minus 1 equals 2. I'm going to rush through the next few steps, but it's just basic manipulation. C minus 1 equals 2 over quantity d minus 1, c equals 2 over quantity d minus 1 plus 1, c equals quantity 2 plus d minus 1 over quantity d minus 1, c equals quantity d plus 1 over quantity d minus 1. If we say d minus 1 equals k, we get c equals quantity k plus 2 over k. We can see as the value of k increases, the plus 2 makes less and less of an impact. C approaches k over k, which is 1. What this means is we want a very low value for k. We can't have 0 because that's an error, so let's try 1. 1 plus 2 over 1 equals 3 over 1 equals 3 equals c, and d equals 2. Since c and d are random variables, we should be able to switch the values and have a correct equation. If d is 3, k is 2, 2 plus 2 divided by 2 is 4 over 2, or 2, with the value of c, so that checks out. Now, if d equals 3 gives us c equals 2, and c decreases as d increases, and c can never equal 1, then we know the largest acceptable integer value of d must be 3. Thus, so ergo ipso facto, therefore hence, a or b must be 1, c and d must be 2 and 3, and the remaining number must be 5. Now, I've been focusing on only one equation for this entire video, a plus b equals c times d, but there are plenty of other equations which have transposable pairs. I've done very little research into this, having only discovered it a week ago, but I guess there's an infinite number of equations which can be solved with transposable pairs. If you can think of any and some of their pairs or methods of deriving those pairs, I'd love to see them in the comments. I'm especially interested in finding an exponential equation with at least one set of pairs. For now, though, I'll leave it at that. Thanks for watching, and have a nice day.